Okay, welcome to RCC short note series. Today we are going to see about working stress method short note. Okay, so working stress method. Okay, working stress method. Here I am going to first teach introduction. Introduction about working stress method. The second one is analysis of assumptions. Assumptions on working stress method. This is a working stress method. Okay. Third one is analysis of working stress method. Okay, so first we are going to see the introduction about working stress method. So each and every point that I am going to teach in the introduction part is important for your examination. Okay, so introduction. So this working stress method also called elastic method or modular ratio method. Modular ratio method. Okay, this is the first point. And the second point is it is based on working load only. Working load only. Okay. Next point is it is based on only working load. We are not considering any factor safety. Okay. The next one is it is quite safe. Quite safe in service condition. In service condition, very safe in service condition, but it is not reliable. It is not reliable on collapse condition. Not reliable on collapse condition. Okay. The next point is working stress method. Working stress method. No correct correlation between various types of load acting at a time at a time on a structure. That means the relationship between the existence of combination of dead load, live load, wind load, earthquake load, snow load, that condition. There is no correlation between various types of load which is acting on a structure. We are not taking into account that. Okay. Next one is FOS, factor of safety. Factor of safety is too high. Factor safety is too high means factor safety for concrete in flexure is equal to 3. Factor of safety for concrete in axial compression is equal to 4. Now factor safety for steel is equal to 1.8. So this is the factual data. You will get a question from this. Keep this factor safety in your mind. Okay. The next point is the strength of steel is the strength of steel is not fully utilized. Not fully utilized. That is only 56 percentage of strength of steel is utilized. 56% of strength of steel is utilized. 56% of strength of steel is utilized. Okay. The reason is since we know that sigma st actual stress divided by we are using the factor safety, that is 3. So it is approximately you'll get 0.555. Okay. Sorry, this is 1.8, right? So that is 1 divided by 1.8, 0.55. Okay. So sigma xt, we take as the factor safety. See, factor safety for steel is 1.8. So this is a distance 0.56 sigma st. That means for design we are considering only 56 percentage. In percentage, if you consider, then this becomes only 56 percentage. Remaining 44 percentage of stress we are not consider. That's why this point says the strength of steel is not fully utilized. Okay, that's a point. Next one is in working stress method, the thickness of steel is the thickness of steel is sorry working stress method, the thickness of RCC member is too high as compared to limit state method. Okay, next one is working stress method, also called modular ratio method. Thus, since steel is transformed into equivalent concrete by multiplying modular ratio of the modular ratio to the steel area. Here, the transformed section AC is equal to area of concrete, which is equal to M times the area of steel. So this is the transformed section area. Okay. Now see, the next one is strain compatibility. Very, very important point. Strain compatibility. Strain compatibility is whole squared in tension zone. In tension zone. Okay, means where Hooke's law is valid is valid and strain in steel is equal to strain in concrete surrounding this steel. Okay, the meaning, so for example, this is the steel. Okay, steel, and above you are having a concrete, and below also you are having a concrete. Okay, this is the concrete. Strain compatibility means when this is the bar, okay, when this bar is subjected to a tensile force, then because of this tensile force, the bar subjected to elongation, the same elongation will be occur on the surrounding concrete. These two are the surrounding concrete. Therefore, equal amount of elongation will be takes place on both ends. Okay, this concept is called as strain compatibility. So strain compatibility means the strain in steel and strain in concrete both are same. That is the meaning. Okay, now strain compatibility means compatibility means strain in concrete means strain in concrete is equal to strain in steel. Okay, now this is the thing. Now we can, based on this, based on strain compatibility, strain compatibility, we can transfer a RCC member into a equivalent concrete section, into a equivalent concrete section, RCC section. Okay, RCC section in the equivalent concrete section. So for example, suppose there was a concrete element, this is the section, and this is where area of steel. And in this case, above the neutral axis, this is the area of the concrete, and below the neutral axis, we will say this is the area of the steel. This is the area of the steel, AST. Now, if we convert the entire area into a equivalent area of concrete, then this area becomes as, this is the transformed section area. This area becomes as is something like that. This is the equivalent section. That means here area of the steel is increased. So this portion is the area of steel. This portion is the area of steel. Okay. Now here area of concrete is equal to m times the area of steel. We converted this area of steel into area of concrete. Now this is becomes as area of concrete, which is equal to m times the actual area of steel. At the same time, stress in steel on this area, stress in steel is equal to stress in concrete divided by modular ratio. Very, very, very important examination question. Keep in your mind to convert um, normal section into, that is RCC section, into equivalent section. Okay, then you have to multiply with the area and divide it with the stress. Okay, so we can say this is the actual RCC section and this is transformed section. Transformed section. So that is the difference. I hope you understood. Okay. Now see the strain compatibility equation, which is used for transforming one section into another section. Okay. Now note note even though this working stress method having many disadvantages till now, even though even though working stress method having so many drawbacks so many drawbacks, but at the present at the present in India it is used it is used in three areas of design. Three areas of design. One is RCC bridges. So the code is Indian Road Congress 21. Second one is RCC water tank. RCC water tank, that is Indian Standard 3370. And the third one is RCC chimney. RCC chimney IS 4998. Okay, so these all are about the introduction part. The second one is that we are going to see assumptions on working stress. So this assumption is also important as per your examinations. Assumptions made on working stress method. So what are the assumptions that we are going to see now? Okay, the first assumption is the plane section remains plane before and after loading. Plane section remains plane before and after loading. This is the first assumption. Means here meaning is means the strain diagram is linear. One time this question is asked. Plane section remains plane before and after loading. Means after loading means the meaning of this statement is strain diagram is linear. So see, initially there was a beam. Okay, and initially this section is a plane section. After loading or after bending, so this is the initial position of beam, and finally the beam becomes something like that. And after bending also the section is remains plane. The section is remains plane. So that is the meaning. So this is the initial state, this is the final state. The meaning is the strain diagram is linear. This is the strain diagram. And the next point is the tensile stress developed in concrete is entirely the tensile stress developed in concrete is entirely resisted by tension steel. Entirely resisted by tension steel only, and none by concrete. None by concrete is only for cracked section. For cracked section. See, the tensile stress developed in concrete is entirely, that is developed in RCC member. RCC, okay, RCC is entirely rested with tensile steel only, none by concrete. Okay, what is the meaning of cracked section? Because of the load, there was a crack. A small crack will be developed at the bottom tension zone. That is a cracked section. Now we can write, take a note. Take a note. First point, for uncracked section, for uncracked section, tension force is taken by tensile steel as well as concrete. Concrete tensile capacity is what? FCR is equal to 0.7 root of FCK. So be careful. For cracked section, the tensile load is tensile stress is taken by only tensile steel. For uncracked section, the tensile force is taken by tensile steel as well as concrete. This is a very, very important assumption. The next one is stress versus strain. Stress versus strain diagram of steel and concrete are linear. What is the meaning? This is the stress versus strain for concrete. This is the strain. This is the stress. And we are assuming the stress versus strain diagram is linear. This is for concrete. At the same time, stress versus strain for steel, also we are considering a linear. This is also a linear. Stress versus strain also linear. This is for steel. Okay. So these are the assumptions that you have to keep in your mind. Okay. Now, the next one is we are going to see the analysis of uh, working stress method. First one, analysis. Okay, working stress method analysis. So first of all, we are going to see the analysis, working stress method analysis. Okay, third topic, working stress method analysis. In the working stress method analysis, what are the things that we need to understand? Critical neutral axis, that is XC, actual neutral axis, that is XA, then under reinforced section over reinforced section then balanced section. Balanced section. So these five is important. Out of this five, these two are important. These three are classified based on these two, critical and actual neutral axis. Now we are going to see one by one. First, let us explain balanced section. Balanced section. Okay. So for that, first of all, we have to draw a diagram, and this is under reinforced section. Under reinforced section. Next one is over reinforced section. Over reinforced section. So these three sections we will look one by one. So first of all, we have to take a beam section of size this is the breadth B, and somewhere here we are having a steel, okay, and from this point to the center of the reinforcement we can call it as D, effective depth. Okay, now you have to project this line, top and bottommost line, to make sense analysis easier. And this is center line of the steel. Okay, now the analysis for the balanced section. Okay, in the balanced section, the concept is the steel and concrete attains a stress equal time or simultaneously. So neutral axis goes somewhere here. This is the neutral axis. And the stress block, which will be something like that. This is the stress block. In the balance section, the stress in the steel and stress in the concrete both will be occur simultaneously. So here for balance section is a characteristic bending compressive strength sigma CBC, and this one is sigma ST divided by M, and this area we can take it as M into AST. Okay, now the total, this is the compressive zone, this is the tensile zone, and the force which is acting on the tensile zone is T, and the force which is acting on the compressive zone is C. Okay, now in between these two, this distance, the distance between these two forces, lever arm, which is equal to D minus total depth is D minus XC divided by 3. How? Let me explain. From this extreme fiber to the neutral axis distance, we call it as XC. And this point, the centroid of compressive force which is acting is XC divided by 3. So this is about the diagram. Okay. Now see, we are going to calculate the critical neutral axis. Okay. By similar triangle principle, similar triangle principle, okay, from similar triangle principle, you will get XC is equal to M into sigma CBC the whole divided by sigma ST plus M into sigma CBC into D. You have to keep this in your mind. Very, very important formula. This is the first formula. You just keep in your mind. This is the critical neutral axis. Also, we can write Xc is equal to K into D. Now, K is equal to M sigma CBC sigma ST plus M into sigma CBC. Okay. Now, put M is equal to, we know the modular ratio 280 divided by 3 sigma CBC. If we substitute this in the XC, therefore XC is equal to, XC becomes 280 divided by 280 plus 3 sigma ST into D. Into D. Now, from that we can conclude XC, which is depends upon only grade of steel, not grade of concrete. See this equation, it is depends upon only the grade of steel, not grade of concrete. This is also an examination question. Okay. Now see, next we are going to see limited. This is a balance section. Therefore, from the balance section only you can able to calculate all limited things. Limited percentage of PT. PT calculation. What is PT? Calculation. Okay. What is PT? PT is percentage of tensile steel. So that is a PT. Okay. Now here we can write compression, which is equal to tension. For calculating this limited PT, you have to equate compressive force equal to tensile force. What is a compressive force? 1 by 2 sigma CBC into XC into B, which is equal to M into AST into sigma ST by M. Stress in the area. This is the stress, this is the area. And compressive force is C, area of the stress block, half into base into height into the stress block is acting throughout the width of the beam. Therefore, I multiplied that also. Okay. So from that, if you simplify this, then finally you will get sigma CBC K divided by 2 sigma ST, which is equal to AST divided by BD. So this is the final value. Now we can calculate this is the PT, right? Therefore, PT, which is equal to K sigma CBC divided by 2 into sigma ST into 100. So this is PT limited. So I can write PT limited. At a critical point, PT you will get a limited. Very, very important formula this. Now what we are going to do, PT actual. Okay. PT actual means PT actual, which is calculated as AST divided by BD into 100. This is the actual, this is based on stress, this is based on the cross sectional area. So generally the PT is calculated based on the area, calculated area. So these two formulas are very, very important. This is based on the limited stress. This is actual means this is based on the actual area. Okay. So Still continuing the balance section. So first we will finish the balance section. From that balance section only you will get more things. Now again, this is okay. Now we are going to look critical neutral axis. Critical neutral critical neutral axis. The critical neutral axis calculated by XC. Okay. Now critical neutral axis. Sorry, critical neutral axis we already finished. This is the critical moment of resistance. Critical moment of resistance. Critical moment of resistance, that is MR. And before that I wanted to say here XC means where XC is critical neutral axis. Okay, be careful. Now see, this is the critical moment of resistance. So the critical moment of resistance which was taken from two sides. One is case A, moment from concrete. If we take moment from concrete side, okay, moment from concrete side, that means if you take moment from C to T, therefore C into lever arm. Okay, therefore moment of resistance which is equal to C into lever arm. Now what is a C? Half into sigma CBC B into XC. So this is the moment, force. Lever arm is D minus XC divided by 3 in the critical section. And we know that 1 by 2 sigma CBC B into what is XC? K into D. XC is equal to K into D minus K into D divided by 3. So if you take out 1 by 2 sigma CBC D common, B D square K into 1 minus K divided by 3. So is equal to 1 by 2 sigma CBC into B D square K J. So this is the moment of resistance. So moment of resistance from compressive zone or concrete is equal to 1 by 2 sigma CBC Kj BD square. So moment of resistance which is equal to, we can write Q BD square. Very, very important relation. This relation you have to keep in your mind. Okay. And where Q is equal to 1 by 2 sigma CBC Kj. K already you know. J is equal to what? 1 minus K divided by 3. Okay. Now Q is moment resistance factor. Moment of resistance factor. Q is moment of resistance factor. J is neutral axis depth factor. Neutral axis depth factor J. Okay. Now see, these are the important formula you have to keep in your mind. Wherever I put the formula in the box, those things only they will ask you in the examination. Okay. Okay. The next one is under the balance section. Under the balance section, why I'm doing the balance section first? Because the balance section is the one which can make sense you other sections. Okay, once you have an idea about the balance section, then only you can able to understand what is the under reinforced or reinforced, so on and so forth. Okay, now area of tension zone. Okay, if you take this is B, B moment from tension zone. Tension zone. If you take moment from tension zone, then what will you get? Moment of resistance which is equal to sigma st stress in the area into d minus xc divided by 3. This is the lever arm, right? See this one? Force into tension into lever arm. Take moment from tension zone to this force, compressive zone. So sigma st ast into d common 1 minus k divided by 3. Since we know that x is equal to k into d, this is the moment of resistance. Moment of resistance is equal to sigma st ast d into j. Okay. Now what is ast? Moment of resistance divided by sigma st dj is equal to ast. So this is the ast. Now the ast which is for the balance section. AST which is calculated based on the balance section is this is the formula. Okay. Now what we are going to do, okay, is the AST. Now let me explain this thing through a example. Okay, through example how the thing is happen. Listen, let us take an example to make sense this. Suppose there was a section. I'm not changing the section. The section is this one 200 by 200 by 300. Let us take the 300. Size is 300. Okay, 200 by 300 and M20 concrete and Fe 415 steel that we are using. In the balance section, suppose if we use 3 bars of 20 mm diameter, this AST, if we use it, then what is the neutral axis depth? XC. Okay, now this can be calculated as, listen, you can able to calculate now the tension force. What is the tension? Sigma st into ast. What is sigma st? Is 415 divided by 415 divided by 1.8 into ast 3 times the 5 by 4 into 20 square. Okay, you know, for this Fe 415, sigma st equal to approximately 230. That means 415 divided by 1.8. So I'm directly putting here 230. So this is 230. So if you calculate it, then you will get approximately this is 216769.89 Newton. This is the tension. Okay. Now in equilibrium, in equilibrium, in equilibrium, tension is equal to compression. We know that in equilibrium, compression is equal to tension. What is the compression? 1 by 2 balance section sigma CBC XCP, which is equal to 216769.89 Newton. So everything you know. What is xc? Xc is equal to 216769.89 Newton, the whole divided by into 2. This 2 goes here, into 7 into 200. Breadth is 200. So sigma cbc for m20 concrete, how much? For m20 concrete, sigma cbc is equal to 7. Okay, therefore finally you will get an answer xc is equal to 310 approximately mm. So your critical neutral axis is 310. 310 is the neutral axis critical. So this distance is, as per the example, is 310. Okay, now what we are doing, the same example, if you reduce the, by keeping all others are constant, by reducing, if you reducing the steel area, then steel fails first. Excuse me, listen. In this case, in the balance section, steel and concrete fails simultaneously. Now what we are going to do, all others are same. I am using AST is equal to, I am reducing the area of steel. 2 bars of 20 mm diameter. I am reducing the area of steel. I am reducing the area of steel. Then what will happen? The steel fails first. Now, what is the compression is equal to tension? We know that the compression is equal to tension. Here also maintain the equilibrium. So this is 1 by 2 sigma CBC into XC into breadth. Here XC not, here XA, actual case. Okay, in actual case, XA into breadth is equal to sigma ST into AST. What is a sigma ST? 230. What is AST? 2 into 5 by 4 into 20 square. So this is 0.5 into 7 into XA, 0.57 into XA into 200 into 7, okay, into XA into 200. So finally XA that you are getting is equal to approximately 207 mm. 207 mm. So be careful. 207. Now what happens? See, in this diagram, because of reducing this area, this neutral axis, in order to maintain the equilibrium of this section, this neutral axis went somewhere here. This neutral axis shifts upward. This neutral axis shifts upward. This is the neutral axis. Now moves upward. So for under reinforced section case, this is the area of concrete. And below that, there is no area. Below this, only the steel takes the stress. Now, in this case, let me draw the stress distribution diagram. Actually, excuse me, listen carefully. Let me come back. This is the stress distribution diagram for balance section, for example. This is the stress distribution diagram for balance section, the same. Now, because of reducing the steel area, your neutral axis shifts upward. So this is the neutral axis. And the concrete is attains the stress less than the actual stress, but the steel only attains the stress first. Why? Because the area is less, so the steel yields first. So the stress in steel is equal to sigma st by m. But you know, stress in concrete, actual stress in concrete is only this much is subjected to concrete. The concrete will not attain its full stress level. Okay, this is sigma cbc dash, sigma cbc dash. But this entire thing is, sigma CBC. This is sigma CBC dash. Okay. Now this is the actual neutral axis, XA, actual neutral axis. Okay. Now from this neutral axis to this distance, we can call it as D minus XA. Then the lever arm, you know. Okay. Now see, now here area of stress block is only this much portion. Only this much portion. This is the area of stress block. Okay, so I'm not confusing this by making this diagram, but I hope you understood, right? So the stress block, actual stress block is this one. Okay, now let us take the next example. Okay, suppose this is the bifurcation point, that is a balance section. If we increase the area of steel, AST, year 3, then you have to increase 4. In that 3, if you reduce it, the steel, then it becomes under reinforced. If you increase the area of steel, then it becomes a over reinforced. 4 bars of 20 mm diameter. 20 mm diameter. We know that C is equal to T. So 1 by 2 into XA sigma CBC into B, which is equal to sigma ST 230 into pi by 4 into 20 square into 4. So finally, you will get a XA, which is equal to approximately 413 mm. Think about it, 413 mm. Means for over reinforced section, this neutral axis, for over reinforced section, your neutral axis value comes down. So this is the neutral axis. The neutral axis shifts downward. This is the neutral axis somewhere here. The neutral axis comes down. So this is our neutral axis. This is our neutral axis. Here the neutral axis shifts down from the original. So here the neutral axis comes down. Therefore now this entire area is the area of concrete for over reinforced section. For over reinforced section, this is the area of concrete. Okay, now the stress block is something like that. Excuse me, listen carefully. This is the stress block of over reinforced section. Stress block of over reinforced section. Over reinforced section. Now, because of the stresses, the steel area is more. The steel takes only lesser force or lesser stress than concrete. Here concrete attains the maximum value, but the steel attains the lesser value than the concrete. So here the concrete stress is full. It attains full value, sigma CBC. So the concrete fails first, but the steel only takes less value than actual. So this stress is sigma ST dash divided by M. So this value is lesser than original, but actual value is what? Sigma ST by M. In the over reinforced section, the steel is not attains the full value, but the concrete attains the full value. Okay, for making this understandable, I taken this example. Okay, numeral example. Okay, now we are going to see one by one the under reinforced section, what are the important points, and over reinforced section, what are the important points. So first of all, we are going to see for under reinforced section, whatever till now we having seen, that I am going to write. Each and every point is important for your examination. Okay, now see the first point I am going to write whatever we have done till now, that I am going to write. First point, steel attains its maximum value, is maximum permissible stress, attains its maximum permissible stress earlier than concrete. See here the steel attains the full value than the concrete. Okay, now second point is because the steel attains the maximum stress earlier time, steel fails first. Steel fails first, but the concrete won't fail. Okay, the steel fails first. The next point is under this, concrete attains a stress value of sigma CBC dash, which is less than actual value. Sigma CBC is the maximum. Okay, less than this one. Now, next point under this is type of failure is call it as type of failure is called ductile failure. This is also important examination question. Ductile failure. Type of failure is called ductile failure, and the neutral axis x actual neutral axis is less than xc. See this diagram? This is the critical neutral axis. Critical neutral axis is this one, right? xc. But xa is less than xc. So xa is less than xc. Now next point is xa is less than xc. What is the meaning? Actual neutral axis lies above critical neutral axis. Here the actual neutral axis lies above the critical neutral axis. Excuse me, listen. This statement also important examination question. In the under info section, the actual neutral axis shifts above the critical neutral axis. This is the critical neutral axis. From the critical neutral axis, the actual neutral axis shifts or moves upward or lies above the critical neutral axis. That is a point. Actual neutral axis lies above the critical neutral axis. Okay, this is the important point. Now, percentage of steel actual percentage is what? Less than PT balanced or critical balanced. This one is the actual. This is the limited or balanced. Okay, we can write it limited. This is the limited. Okay, or you can say this is the balanced also. So PT is less than PT limited. So what is the meaning? AST divided by B into D into 100. This is the actual. Less than, what is the critical? Or balanced, K sigma CBC divided by 2 times the sigma ST into 100. So this is the value. Okay. Next point is compression area. Compression area of concrete is less than compression area of balanced section. See the diagram. In actual under info section, this blue color is the compression zone area, but in the balance section, only this much part up to this balanced neutral axis. This is the area, compression zone area. Therefore, the under info section compression area is less than the balance section compression area. Okay, that is a point. Now lever arm is greater than lever arm of balanced section. This is under reinforced section. That means what is the lever arm formula? That means D minus XA divided by 3, which is greater than D minus XC divided by 3. We know that XA is less. Therefore, after simplification, you will get this is more than this one. Okay, but what is the thing? Moment of resistance. MR means moment of resistance of under reinforced section is less than moment of resistance of balanced section. As compared to balanced section, the under reinforced section moment of resistance is less. Okay, so this is the balanced. So that is a point. Now we are going to calculate the moment of resistance calculation. Okay, before that, actual neutral axis calculation. What is actual neutral axis calculation? So this is calculated based on area of section, first moment of area of section about neutral axis. Based on the moment area techniques, we are going to calculate actual neutral axis. But the critical neutral axis will be found based on the stress block. Based on the stress block, the limited stress block, we calculate the critical neutral axis. Actual neutral axis calculated based on the first moment of area. So first moment of area Bxa square divided by 2, which is equal to MAST into D minus XA. So how? First moment of area about neutral axis. Excuse me, listen. This is the under reinforced section area. Breadth into XA, you will get a area into moment what? Centroid of this point into neutral axis. Okay, XA divided by 2. This is the neutral axis. XA divided by 2. That's why I have written Bxa into XA divided by 2. Similarly, take moment from below the neutral axis. This area is M into AST, and from this point to your neutral axis distance is what? D minus this XA. Okay, so that's why I have written. Now, moment of resistance calculation. Moment of resistance calculation we can take from tension side. From tension side. If you take moment from tension side, then moment of resistance is equal to stress into area, you will get a force into D minus XA divided by 3. Okay, now if you take moment from concrete side, then moment of resistance, which is equal to, we know that 1 by 2 into sigma CBC dash. Be careful, because in the compression zone only this much portion only stressed, not fully stressed. Okay, therefore sigma CBC dash into XA into B into D minus XA divided by 3. So here this sigma CBC is calculated based on similar triangle principle. For XA, your value is sigma CBC dash, but for D minus XA, your value is sigma ST divided by M. Okay, so in this diagram, for D minus XA, your value is sigma ST by M. For XA, your value is sigma CBC dash, and everything you know, you substitute, you will get a sigma CBC dash. Okay, so this is about the balance section. Sorry, under reinforced section. Now the over reinforced section. Important points that we are going to write the over reinforced section. The first one is, here steel attains the maximum permissible stress earlier than the concrete, but here concrete attains its maximum permissible stress. Attains its maximum permissible stress earlier than steel attains. Earlier than steel attains. That means here the concrete first attains the maximum rather than the steel. Okay, so therefore concrete fails first. Here steel fails first. Here concrete fails first. Okay, and the next point is, here we can say steel stress that is, which is less than sigma ST dash divided by M, which is less than sigma ST divided by M. But here is concrete value. concrete is not attains the full stress. That's why the steel is failing. Here, because of increasing the steel area, steel not attains the maximum stress rather than the concrete attains the maximum stress. Therefore, the concrete is fails. Steel's having a stress which is less than actual stress. Okay, so actual stress is sigma st by m, but steel actually attains sigma st dash divided by this. Now we are going to see the type of failure is called here. Type of failure is what? Ductile. Here type of failure is called brittle because this concrete is fail, right? Because concrete is failing, therefore brittle failure. The next one is here neutral axis. Actual neutral axis they are less, here greater than xc. See this diagram. In this diagram, this is your actual, this is your critical, sorry, and this is your actual. And the neutral axis shifts downward. That's why xa is greater than, here xa is greater than xc. Understood? Now, the next point is you can write actual neutral axis, actual neutral axis lies below critical neutral axis, right? So from the diagram, you conclude actual neutral axis lies below the critical neutral axis. This is the actual neutral axis lies below the critical neutral axis. Okay, the next one is PT for actual. Yes, here 4 steels are used. I explained in the example is greater than PT limiter. Okay, therefore AST divided by BD into 100 in this case is more than K sigma CBC divided by 2 sigma ST into 100. Okay, and the next one is compression area of concrete which is greater than compression area of steel. Compression area of not steel, sorry, balanced section. Excuse me, listen. Compression area of in the over reinforced. This red, entire red is the compression area of over reinforced section. But what is the compression area balanced? Only this much area, only this white portion. Okay. So that is an important point. The next point is here the lever arm for over reinforced section is less than lever arm of balanced section. Okay, that means lever arm is what? D minus XA. Because of this XA is greater than XC, anyhow this is less, right? Then ln D minus XC divided by 3. I hope you understood. Because of XA is greater than XC, this entire value becomes less. Okay, and the next point under this is moment of resistance here is less than this over reinforced section is greater than moment of resistance of balanced section is balanced section. Then actual neutral axis calculation. The actual neutral axis only calculated for under and over reinforced section. Okay, calculation. What is the actual neutral axis calculation? The same formula B into XA square divided by 2. Take a moment about neutral axis from the compression zone. From the tension zone, take moment about neutral axis. D minus XA. Therefore, moment of resistance calculation. Next is moment of resistance calculation. This is the actual neutral axis calculation. Moment of resistance calculation from tension side. From tension side. From tension side, what? moment of resistance is equal to sigma st dash into ast into d minus xa divided by 3. Why sigma st dash? Since the entire tension steel is not subjected to limited stress. That's why. Now it can be calculated from this equation xa sigma cbc maximum, but d minus xa, which is subjected to only sigma st dash divided by m. Okay, from that, see this diagram for xa, sigma cbc, for xa sigma cbc, for this is d minus xa, for d minus xa is sigma st dash divided by m. Okay, from that you can conclude what is sigma st dash. Then if you take moment from compression side, then you will get moment of resistance which is equal to half into sigma cbc into xa into breadth into d minus xa divided by 3. Okay, if you substitute, then you will get an answer. So you have to use any one of the formula, either of the formula which gives the same value. Okay, so you can use either this formula or this formula. Both are gives the same value. Okay, don't worry. So this is the answer. And I'm saying the generally we will design the under reinforced section, not over reinforced section. Why under reinforced section? Since the under reinforced section is a ductile failure, so it gives warning. But the over reinforced section is a brittle failure. While failing, it will not give any warning. Okay, so that is about the working stress method basics. You just go through this, you will get idea 2 to 3 times. You have to watch this video and notes so that you will get. Okay, so thank you. We will see the next limit state short notes, limit state method short note. Okay, thank you.